So we call upon Nitzan Aframian.
We didn't practice.
You just sit down. Nitzan?
Nitzan?
Nitzan, please tell us about yourself. Maybe we just make some room.
Okay. So,
Please.
hi, I'm Nitzan. I was born in Jerusalem and I now live in Tel Aviv with Aya and our baby boy Tammuz. I was attracted to science from a young age, and I think my first exposures to science were through TV shows for kids that actually had some prominent scientific themes. So for instance, in Spider-Man, Peter Parker gets bitten by a mutant spider and their DNA somehow recombines. There was Teenage Mutant Ninja Turtles and Mutant, it's even in the title. And there were many more examples like these. I think this really shows the wide-ranging impact of scientific breakthroughs, specifically in molecular genetics in these cases. Anyway, these science themes really captured my imagination as a kid, and it probably also helped that both my parents are in biology-related fields. Today I study interactions between bacteria and the viruses that infect them. Maybe you think of bacteria and viruses as kind of in the same category, just things we should avoid by Tammuz. Maybe you think of bacteria and viruses as kind of being in the same category, just things we should avoid, but these are really very different. Bacteria are living single-celled organisms, and viruses are just parasites, which can only grow and reproduce by hijacking the biological machinery of their host. And all organisms are really plagued by viruses, and bacteria are no different. They also have viruses that attack them. But why, of all things, study interactions between bacteria and their viruses? Well, one reason is that this is a relatively simple system. For comparison, when trying to study interactions between humans and their viruses, this can be much more difficult because we are very complex organisms. And the hope is that by studying a simpler system, we might be able to gain some insights which will turn out to be more widely applicable. Crucially, even though this is a relatively simple system, it still holds a lot of complexities within. Specifically, I'm interested in the social aspects of this conflict. It turns out, perhaps surprisingly, that both bacteria and their viruses use strategies like communication, cooperation, and even altruistic self-sacrifice within this ancient and ongoing evolutionary war. One striking example is that some bacteria, once infected, will commit suicide, thereby killing themselves, but also eliminating the virus that's inside of them. In this way, the individual infected bacteria dies, but it also prevents propagation of the virus to the rest of the bacterial community, thereby saving it from a mass infection. Another example from the virus point of view is that it was shown that some viruses can communicate in order to make collective decisions of whether to remain dormant inside their host or exit and find a new one. So these are both examples of avenues of research that we are involved in my lab, in our lab. My hope for the future is that by studying this simple yet rich system, we might be able to gain some insights into fundamental principles of communication and cooperation in virus-host interactions and maybe even between biological entities in general. So I want to thank the Adams family for this fellowship and the scientific committee, and thank you for listening.
Thank you.
My name is Amir. I'm a physics PhD student at Tel Aviv University under the supervision of Professor Moshe Burshtein, who was actually awarded this fellowship 15 years ago. I'm not present because I'm currently on a vacation in Iceland, but I would still like to tell you a little bit about myself and about my research. I was born in Tel Aviv in 1992 and grew up in Herzliya with my two parents, Vered and David, and my younger sister, Tal. I grew up in a house of engineers. My mother is an industrial engineer. My father is a professor of electrical engineering, also at Tel Aviv University. And with such a background, my path was quite clear to me, and I decided to study physics and electrical engineering at the Technion for a bachelor's. And that was before my army service. I then went on to serve for 6 years as an engineer in the intelligence corps. And I really enjoyed this job, but ultimately I decided I'm more interested in physics and understanding the fundamentals of the world around us rather than engineering, which is trying to take these principles and apply them for practical applications. And that's why I decided to go on with physics, which is what I'd like to tell you a little bit about now. This video was recorded using my computer, and of course all of you are familiar with computers, but what perhaps some of you do not know is that if you look close enough inside your computer, you will see that it is built out of tiny particles like atoms and electrons, which behave very differently from big objects that are around us. So to give an example, if I take a ball and throw it at the wall, obviously the ball will bounce back. But if I take an electron and throw it at the wall, it could, in principle, there is some probability it will go right through it. And it is not just that, even the mere position of this electron is actually not well defined, because this electron can actually be simultaneously in many different positions. Now, this might sound like science fiction, but in fact, without understanding these laws, we would not have been able to build phones, computers, or any other object with electronics in it. And this is all thanks to quantum mechanics, which studies the behavior and the weird laws of these very small particles. Now, in general, when we do physics, and specifically also quantum mechanics, we need to do two things. We need to perform experiments, and we need to explain what we see in the experiments using theory. It could also go the other way around, where we predict some effect using theory, and then go to the lab and try to look for this effect in an experiment. Now, the problem is that nature is messy, and it is very difficult to observe a specific effect and isolate it from other effects which are around us, noise, and any other disturbance you can think of. And that is why in the past 30 or 40 years, people started to think about what is called quantum simulators, which are artificial devices which are built in a lab. These simulators mimic the behavior of a specific model or a family of models in a way that is very sterile and controllable. And this allows us to basically isolate a specific effect we're interested in without being disturbed by other effects, noise, and so forth. So that is my, in very broad terms, what I do in my research. And also these simulators require both theoretical understanding and experimental work, and I focus on the theory side of these things. I would like to thank the Adams family for their incredibly generous support and also the scientific committee. I would also like to thank my advisor, Moshe, for his guidance and support that led me to where I am today, and it is really a great honor to follow his footsteps as an Adams Fellow. I hope that, and I will do my best, that my research stays on par with this very prestigious title. With the very high standards that come with this prestigious title. So I'm going to conclude with a few words about the bigger picture, because it is really exciting to take a small part in an endeavor to try to learn more about the world around us and observe new effects that might be potentially be used in actual practical applications in the future. And the holy grail with that regard in my field is a quantum computer, which is a device that can solve problems that are practically unsolvable using regular computers. These quantum computers can potentially lead to real breakthroughs in the worlds of medicine, climate research, and many other fields. So it is really a privilege to take a part in this endeavor, even if it is only a small part. So I'm really looking forward to meeting everyone in future events, and I would like to thank you for listening.
Very nice. So we have a second generation Adams Fellow.
Buonasera. I'm very excited to be here. Actually, I'm in Italy, as you can tell. I'm here because I need to present a paper in a conference, which is a great opportunity to thank the Adams family for supporting this kind of activity. So let me tell you a bit about myself. My name is Shir, and at the age of 8, I really loved cats. I really wanted to have one, and as my parents wouldn't let me, I decided instead to set up a website dedicated entirely to cute photos of cats that I found online. This may sound impressive, but actually I was just copying my older brother's Niv personal website, which also should not come as a surprise as both of our parents, Moshe and Harel, are software engineers. Nowadays, both me and Niv are pursuing PhD in computer science. I studied the Technion, and I also ended up marrying Barak, another graduate student in computer science. Just to be complete here, we also have a younger sister, Keren. She's currently at the army, but well, it does not take all of us computer scientists in the family to prove by induction where she is going to be in a few years. So let's talk about my research. I assume you all save your money in some sort of bank account, but the drawback of banks is that maybe someday the bank will collapse, and this will make us lose all of our money. And this is why in recent years, new solution have arrived. So for example, maybe some of you heard of Bitcoin that uses blockchain technology. And in new solution, the thing is that we don't have a centralized bank, which serves as a single point of failure, but we have a lot of individuals run the system together. So for example, let's assume that we all Adams Fellows want to set up a new system that we run. So I can be here in Italy, you can be in Israel, maybe some of other fellows are in the States as we speak. So what we need to do is first we are going to define a set of rules that we're all going to follow. So for example, maybe we're going to open a WhatsApp chat group and decide that if I want to transfer money, let's say I want to transfer 5 coins to Eliana, I'm going to write a message in the chat about that. And this will work just fine as long as we all actually follow this set of rules. But what happens if some fellows are a bit more greedy than others or a bit more malicious, they want to manipulate the system? So for example, they can transfer money without sending messages, or they can say that they transfer money without actually doing so. So in this case, the system we designed may not work that great anymore. And this is exactly where my research kicks in. I'm trying to see how individuals, or many different individuals, can run a system together when we take away the element of trust in the system. And actually, previous studies have shown that such system can be designed with up to a threshold of the individuals that are not following the rules or being malicious. But I'm trying to optimize such system. So for example, let's say that nowadays cellular package costs so much and we want to save upon our messages, to send as few messages as possible on WhatsApp. Designing such systems will allow us all to actually achieve higher level of trust in our world, because we no longer have this single point of failure. And it will allow us to design scalable, better performant solutions. So just to conclude here, since the age of 8, I learned a lot. I evolved as a person. I learned a thing or two. And nowadays, I actually have a dog. So I'll finish with that. And I hope to see you all in person someday. Enjoy the evening.
Okay, wow. Diploma again.
Okay. Hi everyone, my name is Matan. I'm a PhD candidate in mathematics at the Weizmann Institute of Science under the supervision of Professor Boaz Klartag. My research is in the field of Riemannian geometry. Riemannian geometry generalizes notions from Euclidean geometry, which is the classical geometry we study at school. Euclidean geometry models our notion of a flat space, where parallel lines never intersect, and the sum of angles in a triangle is 180 degrees. However, there are other geometries in which these assertions do not hold true. So, for example, I brought here a globe, a sphere. So the shortest path between 2 points on the sphere is what we call a great circle or a great arc, and any two great circles eventually intersect, so they're not parallel. And if you draw a triangle on the sphere, the sum of angles will be larger than 180 degrees.
Less than 540.
So the geometry of the sphere is different from the flat geometry, and this is some of what we study in Riemannian geometry, different geometries than the flat one. So my research attempts to deduce geometric conclusions from partial metrical data. Together with my advisor, Professor Klartag, we were able to show that it's possible to recover the entire geometry of the Euclidean plane by distances between pairs of points in a relatively sparse set. So to illustrate this, imagine an infinite flat plane. I hope that there would be a flat floor, but it steps here. So imagine an infinite flat plane, and suppose that inside every square kilometer I put a person. Okay, so there are infinite amount of people, but they are very, very far away. And to each of these people, I give a GPS device, like Waze or Google Maps, that can calculate its distance from every other person. Okay, so for example, if I'm a person on this plane, and I say the name of my friend Henry, I say Henry, and the app says back, Henry is 4 kilometers away. So this means if I walk in a straight line towards Henry, at a constant speed of, let's say, 1 kilometer per hour, it would take me 4 hours to reach Henry. Okay, so I have all of these distances. Suppose that I cover the eyes of all of these people, and now I place them in an arbitrary surface. Okay, so this surface, you can imagine some kind of a infinite blanket. It can have hills or valleys, or it can be flat. Okay, and I again give them this GPS device, and again they can calculate the distance between them. So for example, if I'm a person now on this arbitrary surface, I can again say Henry, and the app will say back, Henry is 4 kilometers away. And this now means that if I walk along a shortest path, now this path doesn't have to be a straight line. It can go up hills and down valleys and do some kind of a path. But if I walk along the shortest path at a constant speed of 1 kilometer per hour, it will take me, again, 4 hours to reach Henry. Okay? And together, these people have all of the distances between them. And the question that we ask ourselves was the following. Suppose that the distances between these people on this arbitrary surface were exactly the same as the distances that they measured in the flat case. Okay, so again, if I asked on this arbitrary surface, I said to my app, my eyes are covered, I can't see anything, but I said Henry, the app said Henry is 4 kilometers away, and on the flat case, it also said 4 kilometers away, and this is not only true for me and Henry, for any pair of people, the app says exactly the same thing. What can we conclude from this? Does this mean that the new arbitrary surface must be flat, or could there be a hill that was undetected by these distances? So our result was that yes, this new surface, this arbitrary surface, it must be flat. There are no hills and no valleys everywhere. It must be flat. So just by knowing the distances between us, between all these people on this new arbitrary surface, knowing that these distances are exactly as the flat case, all of the blindfolded people that can't see anything can deduce that they are in a flat plane. There are no hills and no valleys anywhere. And for us, this was quite a surprising phenomenon. And the main focus of my future research is to find whether this happens in other cases, not only the Euclidean plane, Euclidean space, and other spaces. So thank you for your attention. And I would like to thank the Academy's committee for their choice and the Adams family for their generous fellowship. Thank you.
Omer Granik.
Okay.
Thank you. I'm excited to be here at my first Adams seminar. So I'm Omer. I was born 26 years ago in Tel Aviv, and I was raised in a very science-oriented family. So my father, who's there in the crowd, in the audience, Ronnie, is a soft matter physicist at Ben Gurion University. My mother, Gali, she's a historian of modern physics at Weizmann University. So it wouldn't come as a surprise to anyone that I was interested in science basically since I can remember myself. And it means a lot of things. It means that on holidays, the attraction of choice was science museums, of course. And the activity of choice on weekends was looking for a cool sample to look under our recreational microscope or building an electronic circuit with the latest home science kit. So yeah, it really sort of made me interested in science from day one. And I would say that my first encounter with academic research was in high school. So as part of the science major that I was taking, me and my friend were tasked with solving a real-world problem using the tools that we had learned in school, this ultimately led to a 2-year project in which we built a buoyancy control system for professional scuba divers. And back then, I already knew that that is the sort of stuff I wanted to continue doing, scientific research, particularly in physics. And so after my military service in the Israeli Navy, I enrolled for undergraduate studies towards a degree in mathematics and physics at Technion. And this was a wild period of broad scientific exploration for me. I participated in numerous projects, both on Technion campus and elsewhere, in physics and applied maths. But really the project that made me choose a doctorate in physics was the one that I had with my now PhD advisor, Professor Yariv Kafri, at the Department of Physics. And it exposed me to an exciting new field in physics called active matter. So what active matter precisely is, well, it's actually all around us. We are all ourselves active systems. Human beings are active systems. We consume energy by eating and convert it to motion by walking, and hopefully also to other things. And one could say that this defines an active particle. It propels itself forward by consuming energy. And the astounding thing is that even though a human is a very complex system, right, when many humans crowd in the same location, say a music concert or some other mass event, then their collective dynamics can be described by very simple physical laws. And to a great extent, these simple physical laws apply also to schools of fish, flocks of birds, even colonies of bacteria. And I would say that the most shocking fact is that they also apply to non-living systems. So even grains of dust shaken on a surface would follow the same laws of physics as the humans in the concert. So for me, that was quite shocking, and I instantly understood that that's the sort of stuff that I want to be studying. So what exactly I'm studying, where do I fit in this picture? So I would describe my research using the following example, which is sort of an oversimplified example. So imagine an arena filled with active particles, let's say for the sake of the example, humans in a music concert again. Of course, the models that I work with are more precise than this overly simplistic setup. And let's say that we put a sizable object in the arena. So let's say a shopping cart. So we throw a shopping cart and right to the middle of the crowd. And as the people move about in the crowd, they bump into the shopping cart, causing it to move erratically in a random way. And my goal is to predict how exactly what would be exactly the motion of this passive object inserted to an active arena. And this could be anything from a shopping cart in a music concert to a dead cell in the middle of a colony of bacteria. So really what I'm striving is to derive general physical laws that would govern the motion of these objects. And we've already derived several relations. Me and my collaborators, we have 2 papers with a bunch of really cool results which apply to any active system. So it does not depend on whether it's birds or humans. And really, what I like about this sort of thing is that by studying very simple models, we can obtain general physical insight into general systems all around us in our day-to-day life. So yeah, I would like to thank the Adams family and the academic committee and the academy for awarding me this scholarship. Thank you. And I hope this will allow all of us, the fellows, to expand our research and take more risks in trying to answer outstanding questions in science in general. And thank you all for your attention.
Thanks so much. Okay, now, you want to donate something for the Adams program, no?
That's my donation.
Hi everyone, I'm Eliana. I was born in Jerusalem and I grew up here. My parents, Benny and Anita Steinberg, made Aliyah over 30 years ago and are now retired. My dad was a computer programmer and my mom was a book editor. So as you can tell, I'm a little rebellion because I'm the only one in my family that loves science. From a very young age, I was interested in biology, and I always wanted to combine it with the clinical aspect. So therefore, after I finished my bachelor's degree and worked 1 year as a pharmacist, I continued on to earn my master's degree in cancer research. Because I really love my research and I find it to be very meaningful and important, I'm now continuing to my PhD. So as we all know, cancer is a very devastating disease. My research is focused mainly on pancreatic cancer, for which the 5-year survival rate is around 10%. Meaning patients, once they're diagnosed, they don't have a lot of time to try different drug combinations until the right one is found. In many cases, they only find out after a few months that they have resistance to the treatment, and unfortunately, they don't get the chance to try different treatments. And in addition, they suffer through very terrible and horrific side effects because their prescribed treatment is a one-size-fits-all rather than finding them the suitable one that's optimized for them specifically. So my research at Professor Ofer Benny's lab focuses on developing a tumor-in-a-chip model that mimics each patient's cancer for the purpose of determining an individualized and personalized treatment for each patient. Meaning, I work in collaboration with doctors in Hadassah Hospital, and I receive the tumor biopsy after it's resected. So I use the different tissue samples to model the different cancer cancer of the specific patient. And I use the different drug combinations according to what the doctors recommend. So why do we need to do this? Because even if different samples have the same name, such as pancreatic cancer, each patient has a different cancer. So hopefully, once I'm able to optimize this tumor-in-a-chip model, I will be able to research different aspects of this disease. For example, a few months ago, in collaboration with Space Pharma and NASA, we were able to send to space tumors on a chip and investigate the different disease course and if whether drugs work better under these microgravitation circumstances. So thanks to this Adams Fellowship, I will now be able to focus more of my time to this very important research, and I hope to actually contribute in improving the very devastating statistics of pancreatic cancer and different cancers in general. Thank you.